Hello everyone and welcome to 30 days of DSA challenge where we will be solving a DSA problem every day for the next 30 days. So this is our day number 17 and today we are going to solve a problem based on binary search trees and the level of this question is going to be medium. The name of this question is validate binary search tree. You will get this question link in description and you can also download this Excel sheet from description. Now without wasting much time, let's see our question on LeetCode. So here we are on LeetCode. Let's read our question. So the question says, given the root of a binary tree, determine if it is a valid binary search tree or BST. So question is pretty straightforward. Question is saying that I have given you a binary tree and the root of the binary tree. You just have to determine that binary tree is a valid BST or binary search tree or not. Okay, this is our question. And if you are wondering what is binary search tree or what is a valid binary search tree, then here is a definition of BST or binary search tree. But I will explain you the definition of BST by taking some examples so that you will understand it in a more better way. And then we will try to solve this problem. Okay. So firstly, let's try to understand what is BST or binary search tree. Okay. So a BST is nothing but a type of binary tree. But this BST have some extra conditions. Okay. Now, what are those conditions? Let's see this. So see, if we are considering this particular node, if I consider this node 5, okay, then everything which is present in the left subtree, right? Everything which is present into the left subtree of this particular node should have values lesser than 5, okay? So here we have 2, which is lesser than 5. It means that, yes, it is valid, okay? Similarly, if we are considering this node 5, if we are considering this node 5, then everything which is present into the right subtree, right? Everything which is present into the right subtree should have values greater than 5, okay? So here we have 8 and you can clearly see this 8 is greater than 5, okay? So these are the two conditions. These are the two basic conditions for a binary tree to become a binary search tree, okay? And these conditions are valid for each and every node, right? These conditions are valid for each and every node. For example, let's say if right now I consider this particular node, right? If I consider this node number 2, then everything which is present into the left, right? Or everything which is present into the left subtree of this particular node has to be values lesser than 2, okay? But here you can clearly see at the left we do not have anything, or you can say that in the left subtree we have null. So we can say that if in the left I am having a null, right? If in the left subtree I'm not having any particular node, then I can say that yes, it is valid, right? I can say that yes, it is valid. Similarly, if I go into the right subtree, then here also you can clearly see that I have null, right? What does null signify? Null signifies that we do not have any node in the right subtree, okay? And if we do not have any node in the right subtree, then we can say that yes, it is a valid BST, okay? It is a valid BST. So for this particular node number 2 also, the two conditions for BST are valid, right? The two conditions are valid. Similarly, if we consider this node number 8 and if we try to go to the left subtree, so here also you can clearly see that we have a null value. And as I said, whenever we are encountering a null value, it signifies that we do not have any node there. And if we do not have any node present into the left subtree, then we can say that it is also valid, okay? It is also valid. Similarly, if we go to the right subtree, then here also we are having a null value. If we are encountering a null value, it also means that it is a valid BST, okay? So these are the two conditions, right? These are the two conditions that everything which is present into the left subtree should have values lesser than this current node which we are considering, okay? And everything which is present into the right subtree should have values greater, okay? And we have to check these conditions for each and every node present into our binary tree, okay? So let's take some more examples so that you will understand what is binary search tree in more depth. So let's take this particular example to understand binary search tree in a more better way, okay? See, if I am considering this particular node, this node 5, then what I have to check? I have to check that everything which is present into the left subtree, right? You can clearly see that this is nothing but my left subtree, okay? So everything which is present into the left subtree should have values lesser than 5, okay? Should have values lesser than 5. So here we can clearly see we have 3 which is lesser than 5, right? 3 which is lesser than 5. It means that, okay, it is valid. Here we have 2 which is lesser than 5. it means that yes, it is valid. Here we have 1 which is lesser than 5, it also means that yes, it is also valid. Okay, so we have checked for the left subtree. Okay, now what's the next task? Our next task is to check for the right subtree, right? We have to check for the right subtree. So you can clearly see this is the right subtree, and what are the condition for the right subtree? That every value present into the right subtree should have greater value than this 5. Okay, so here we have 7 which is greater than 5, it means it is valid. Here we have 6 which is again greater than 5, it means it is valid. Here we have 8 which is greater than 5, it means again it is valid. Okay, so for this particular node, let me just rub this. Okay, so for this particular node number 5, we have checked that the left subtree, all the values which are present into the left subtree are lesser than 5, and all the values which are present into the right subtree are greater than 5. It means that it is valid, right? It means that it is valid. But now I have to check this condition for each and every node, okay? So now I'll check those two conditions for this node, right? For this node number 3, okay? I'll go to the left subtree, and what is the condition? That everything present into the left subtree should have value lesser than 3. Okay, so here we have 2 which is lesser than 3, it means that it is valid, right? It means that it is valid. Okay, similarly, if I go into the right subtree, then what is the condition? Everything which is present into the right subtree should have values greater, right? Should have values greater than my node. Okay, so here I have 3, here I have 1, right? And you can clearly see 1 is not greater than 3, right? 1 is not greater than 3. What does it mean? It means that it is not a valid binary search tree, right? It is not a valid binary search tree. And whenever we are encountering a single node which is not fulfilling our condition, it means that this whole binary tree is not a binary search tree. So we can directly return false, right? We can directly return false. Okay, so this was a quick introduction about what is binary search tree. Okay, and now if we try to think of how we are going to solve this problem, then the one naive solution which could come into your brain when you see this problem is, see, when we are standing at this particular node, right? When we are standing at this particular node, what we need to check? We need to check that the node which is present into the left hand side, right? The node which is present into the left hand side should have value lesser than this particular node, right? So here I have 3. If I try to go to the left side, then I'm getting 2. Okay, so this 2 has to be lesser than 3. Okay, this 2 should be lesser than 3. If it is, it means that it is valid. And similarly, if I try to go onto the right side, then I have to check that anything which is present onto the right hand side should have value greater than this 3. Okay, so here we are having 1 which is not greater. So let me just write 4 here. Okay, let me just write 4 here. Right, and now if I check the condition, so everything which is present into the right hand side should have values greater than 3. So we can clearly see that this 4 is greater than 3. Okay, this 4 is greater than 3. So now we can say that this particular node number 3 and its left and right subtree are a valid BST, or you can say that this much portion, right? This much portion of our binary tree is valid. Right, this much portion of our binary tree is valid. If it is valid, then what we'll do, we will return true, right? We will return true to the parent of 3, which is 5, right? So at 5 we will return true. Okay, now similarly we have to check for this particular node. So we have the same conditions. Everything which is present onto the left should have values lesser than 7. So we can clearly see that this 6 is lesser than 7, it means that it is valid. And similarly, everything which is present onto the right subtree should have values greater than 7. So here we can see that we have 8 which is greater than 7. It means that it is also valid, right? It means that it is also valid. So if the two conditions are fulfilled, it means that this portion of the binary tree is also a valid BST, right? It is also a valid BST. So we will also return true. Right? Now here at this node number 5, we are getting 2 true values, right? We are getting true from the LHS, or you can say from the left subtree, and we are also getting a true value from the right subtree. Okay, if you are getting true values from both the sides, then I can say that I will return true, and I can say that yes, it is a valid BST. Okay, it is a valid BST. So this was the brute force or the naive solution which could come into your mind when you see this particular problem. But there is a problem with this particular approach. Okay, let's analyze what is the problem. So let's take this sample test case, and let's say that instead of having 6 here, if I have a value, let's say 3. Okay, let's say I am having a value here equal to 3. Okay, And now let's try to check that it is a valid BST or not. Okay, so we will use the same procedure. Okay, let's check for this particular node. So everything which is present onto the left should have values lesser than 3. So we have 2 which is lesser than 3. It means that it is valid. Okay, and if I try to go to the right subtree, then everything which is present into the right should have values greater than 3. Okay, so here I have 4 which is greater than 3. It means that it is also valid, right? It means that it is also valid. So now what we'll do, we can just simply return true. We can just simply return true to the parent. Okay, and now we will try to check this particular node. Okay, so for this particular node we will go to the left, and onto the left what is the condition? That everything present onto the left should have values lesser than 7. Okay, so here we have 3 which is lesser than 7. It means that yes, it is valid. And similarly, if I go to the right hand side or into the right subtree, all the values which are present into the right subtree should have value greater than 7. Okay, so here I have 8 which is greater than 7. It means that this is also valid. Okay, if this is also valid, then what I'll do, I will return true, right? I will return a true to the parent. Okay, and here at node number 5, I can clearly see that I'm getting a true from my left subtree, and I'm getting a true from my right subtree. What does it signify? It signifies that this particular left subtree is a valid BST, and this particular right subtree is also a valid BST. If both are valid BST, then what I'll do, I will return a true, signifying that yes, this complete tree is a valid binary search tree. Okay, but if you see this particular example clearly, if you observe it clearly, then this is not a valid BST, right? It is not a valid BST. Why this is not a valid BST? Why this is not a valid BST? Let's see this. See, here we have 5, right? And as per the condition for a valid BST, everything which is present onto the right should have value greater than 5, right? Everything which is present onto the right should have value greater than 5. So here you can see that we have 3 which is not greater than 5, right? We have 3 which is not greater than 5. It means that this particular node does not follow the rule of being a valid BST, right? And if we follow the approach which we have just discussed, then when we were following that particular approach, when I was doing a dry run for this particular example, there you saw that with that particular approach we were getting a true, right? We were getting a true, but actually we should return false for this particular test case because it is not a valid BST. So there was a problem with our previous approach which we have just seen. Okay, okay, now if we try to solve the previous problem, then how we can solve it? So we can solve it in a way, right? See, we know that in the right subtree all the values should have greater than 5, right? All the values should be greater than 5. So now what I can do, see, if I am standing at this particular node, right? If I'm standing at node number 5, what I'll do, I'll go into the left subtree, right? I'll go into the left subtree and I will try to find out the minimum value which is present into my right subtree. Okay, so here you can clearly see the minimum value is 3. So now I will check this minimum value which is 3. Is it greater than 5 or not? If it is greater than 5, then I can return a true, and if it is not greater than 5, then I can just directly return a false. Okay, so this is one solution, right? So instead of just comparing the immediate right or immediate left node, we have to find out the minimum, right? We have to find out the minimum in my right subtree, and I need to find out the maximum from my left subtree. Okay, and then I have to check that this maximum value, which I'm getting from my left subtree, it should be lesser than 5, and the minimum value which I'm getting from the right subtree should have value greater than 5. Okay, so this is the another approach which we can use. Okay, but there is a problem with this particular approach as well, and the problem is of time complexity. Okay, if we are using this particular approach, so let's try to analyze what will be the time complexity. See, when I'm standing at this particular node number 5, then what we'll do, I will traverse all the nodes present into the left subtree, and I will traverse all the nodes present into the right subtree. Okay, then I will find out the minimum and maximum value, and then I will compare it. Okay, so after doing comparison for this particular node number 5, if I come to this particular node, which is node number 3, then what I need to do, again I need to traverse the left subtree completely, and I need to traverse the right subtree completely. Okay. Similarly, if I'm standing here at this particular node number 7, then again I need to traverse the left subtree and the right subtree. So if you observe this particular approach clearly, then you can definitely find out that the time complexity will be n square, right? The time complexity will be n square, because for each node we are going to the left subtree and to the right subtree. Okay, so you can say that the approximate time complexity will be equal to O of n square. Okay, so this is not a good approach, right? Because the time complexity is of n square. Okay, so let's try to think of, can we solve this problem in a linear time complexity just by doing a single traversal? Is it possible? So the answer is yes, it is possible. Okay, let's take one test case to analyze it. So let's take this particular example to understand how we are going to solve this problem. Okay, so let's say that currently if I am standing at this particular node, so instead of finding out what is the maximum value into the left subtree, what is the minimum value into the right subtree, and then comparing it with the node value, let's try to find out a range. That if this node value is in the particular range, it means that it is a valid BST, and if it is out of my range, then it is not a valid BST. Okay, now how we will think of that particular range? Okay, let's think of it. See, if I'm standing at this node number 6, right, and if I consider this node 7, then this node number 6 is coming into the left subtree of node 7. Okay, it is coming into the left subtree of this node 7. What does it mean? Everything which is present into the left subtree should have value lesser than 7, right? So everything which is present into the left subtree should have values lesser than 7. Okay, so this is the one conclusion which we have drawn, right? Which we have drawn from this particular example. Okay, now instead of considering this 7, let's say that I'm considering this node 5, right? Let's say I'm considering this node number 5. Okay, and this node 6 is coming into the right subtree for this particular node 5, right? For this particular node 5, and as per the conditions of a valid BST, everything which is present into the right subtree should have value greater than 5 if I'm considering this node number 5. Okay, so the second conclusion is everything which is present into the right subtree should have value greater than 5. Okay, and now if I merge these two conditions, so now what I can say that the value present here, right? The value present here, it should be lesser than 7, and it should be greater than 5. Okay, and what is the value present here? The value present here is nothing but 6, right? And this 6, if you see clearly, this particular 6 is greater than 5, and this 6 is lesser than 7. Okay, so this particular node value is satisfying our range. Okay, the value of this node should be greater than 5 and it should be lesser than 7, right? So this was the valid range, and what we will do, instead of finding out the minimum and maximum for each and every particular node, we will try to draw this range. Okay, and if that particular node value is coming into our range, then I can clearly say that yes, it is valid. If it is not coming into our range, then I can say that no, it is not valid. Okay, so this is our approach. Let's say initially I'm standing here at this particular node, and I have a root pointer which is pointing to this particular node, right? And this root pointer signifies that this is my root node, and it also signifies the current node where I'm standing. Okay, so see, if I'm standing at my root node, right, and if I ask you what should be the valid range, right? What should be the valid range for my root node? So you will say that the value of my root node can be anything, right? Because it is not coming into the left subtree of any particular node. It is also not coming in right subtree of any particular node, right? So this node 5 can have any value, right? But still we have to draw a range. Okay, so let's say that the range for this particular root node should be from -infinity, and it should be lesser than the positive infinity. Okay, let's say this is our range, and this node number 5 is coming into this range. Okay, it means that this is valid, right? It means that this is valid. Now if this is valid, so what we have to do, we have to check the left subtree and we have to check the right subtree, right? We have to check this particular node 5 is coming into our range. Okay, but for this binary tree to be a valid BST, it is important that the left subtree should also be a valid BST, should also come into our range, and the right subtree should also come into our range. Okay, so now we will go into our left subtree and right subtree, and we will check that the node values are coming into our range or not. Okay, so let's say now I try to go to the left subtree. Okay, let's say I'm coming here into the left subtree and my root pointer is pointing here. Okay, so root pointer is pointing here. It means that currently I am standing here at this particular node number 3. Okay, now what should be the valid range for this node 3? What should be the valid range for this node 3? Okay, so we know that this node 3 is coming into the left subtree for this particular node number 5, right? It is coming into the left subtree of this particular node number 5. What does it mean? Everything which is present into the left should have value lesser than 5, right? Should have value lesser than 5. So I can say that this particular node value, right, whatever this node value is, it should be lesser than 5, right? It should be lesser than 5. Okay, but what should be the minimum value? What should be the minimum value for this particular node? So you will say that the minimum value can be anything. Minimum value can be anything. So let's say that for this particular node, the minimum value is minus infinity, or from where we got this minus infinity, we got it from here. Okay, we got it from here. So we just copy pasted it here. Okay, we have just copy pasted it here. Okay, now we will check that this particular node value, which is 3, it is coming into this range or not. Okay, so you can clearly see that this particular node value, which is 3, it is greater than minus infinity. Okay, and it is lesser than 5. It is lesser than 5. What does it mean? It means that this particular node is valid. Okay, this particular node is valid. Okay, if this particular node is valid, then now our next task is to go into the left subtree and go into the right subtree and check the left subtree and right subtree node values are also coming into the valid range or not. Okay, so now I'll go to the left subtree. Okay, so let's say here I have my root pointer. Okay, so now if I'm considering this node value, which is 2, right? So it is coming into the left subtree. It is coming into the left subtree of 3. Okay, so the node value which I have here, it definitely should be lesser than 3. Okay, definitely it should be lesser than 3. But if I try to find out what should be the minimum value, what should be the minimum value for this particular node, it can be anything. So let's say it is minus infinity. Let's say it is minus infinity, right? And now we will compare. Okay, so we have this node value as 2. Okay, we will compare this 2. Is it lesser than 3? You will say yes, it is. And this 2, is it greater than minus infinity? You will say yes. It means that this is also valid. Okay, this is also valid, right? And if a particular node is valid, then what we will do? We will go to the left and right subtree of that particular node, right? We will go to the left and right subtree of that particular node. Okay, so if I try to go to the left subtree, so here you can see that we have nothing or we have null, and in the right subtree also we have null. Okay, we have null and we have null here. So when we are encountering a null value, it means that we do not have any nodes present into the left subtree or right subtree. Okay, and if we do not have any node, then we can say that it is valid. It is valid BST. Okay, so from here I will return a true. Okay, from here I will return a true. Okay, so what does this true and true signifies? This true and true signifies that the left subtree is a valid BST and the right subtree is also a valid BST, and we have also checked that the value of this particular node, which is 2, it is coming into our valid range or not. Okay, we have also checked that. So now when we are getting true from left hand side and we are getting a true from right hand side, then what we will do, we will return a true to the parent. Okay, so we will return a true to this node number 3, right? We will return a true to this node number 3. Okay, so for this node number 3, we have checked the left subtree. Okay, and now we have to check the right subtree, right? So now I'll come here to this right subtree, and here I have 4, right? Here I have 4. So firstly I will check that this particular node value is coming into our valid range or not. Okay, it is coming into a valid range or not. Okay, so here you can clearly see that we have a node with the value 3, and this 4 is coming into the right subtree of this node 3. Okay, and we know that everything which is present into the right subtree should have value greater than 3. Okay, so the value which is present here, it should be greater than 3. Okay, it should be greater than 3, right? It should be greater than 3, or I can also write it in this way, right? The value should be greater than 3, right? The value should be greater than 3. But if I ask you, what should be the maximum value for this particular node? What should be the maximum value? See, here if I write 6, it is also valid because 6 is greater than 3. Okay, if I write 100, it is also valid because 100 is again greater than 3, right? If I write 200, then again it is also valid because it is also greater than 3. Okay, so the conclusion is I can write any value here, I can write any value here, but it should be greater than 3, it should be greater than 3. So now what I can say that the value which is present at this particular node should be lesser than positive infinity, right? It should be lesser than positive infinity, because I know that I can write anything here, I can write anything here, so it just should be lesser than my positive infinity. Okay, it can be any maximum value but lesser than positive infinity. And now if you are wondering from where I got this positive infinity, so I got it from here. Okay, when I will write the recursive solution, then you will understand, right? Then you will understand how I am doing this. Okay, okay, so now I will just check that this 4 is coming into this range or not. So if I write 4 here, you can clearly see that this 4 is greater than 3. Okay, and this 4 is also lesser than positive infinity. Okay, so both the conditions are satisfying. Okay, if both the conditions are satisfying, then what we'll do, we'll check for the left subtree and we'll check for the right subtree. Okay, so here you can clearly see in the left subtree and the right subtree we have null values. It means that they are valid, right? So from the left subtree I'll return a true value, and from the right subtree as well I will return a true value. Okay, so I'm getting a true value from both the left hand side and the right hand side. It means that, it signifies that the left subtree is also valid BST, the right subtree is also valid BST, and this particular node value 4, it is also coming into the valid range. Okay, so now what we will do after checking these 3 conditions, right? After checking these 3 conditions, what I'll do, I will return a true to the parent. Okay, I will return a true to the parent. So here at this particular node, we have already checked, right? We have already checked that the value of 3 is coming into our valid range, and we are also getting true from the left subtree, meaning that the left subtree is a valid BST, and we are getting a true from the right subtree, which signifies that the right subtree is also a valid BST. Okay, now if all these 3 conditions are satisfied, right? If all these 3 conditions are satisfied, then what I'll do, I will just return a true to its parent, right? I will return true to 5. Okay, so for this particular node number 5, I have checked that this left subtree is valid, right? This left subtree is valid, right? And now I have to check for the right subtree, right? Now I have to check for the right subtree. So now let's say that I am here in this right subtree, and currently I am standing here at this particular node. Okay, at this particular node. Okay, so see, for this particular node value, which is 7, what should be the range? What should be the range? Okay, so let's analyze. See, we know that this particular node 7, is coming into the right subtree, right? It is coming into the right subtree for this particular node value 5. Okay, so we know that everything which is coming into the right should have value greater than 5. Okay, so I can say that I should have value greater than 5, right? I should have value greater than 5. Okay, but what should be the maximum value? See, instead of 7, if I write 100 here, it is also valid because this 100 is greater than 5. Okay, instead of this 100, if I write 1000, then it is also valid because it is also greater than 5, right? It is also greater than 5. So the conclusion is, or what I'm trying to convey is, here when I am in the right hand side, so the maximum value can be anything. So let's say the maximum value have to be lesser than positive infinity. Okay, and now we will check this particular node value, which is 7, it is coming into this particular range or not, right? So if I write 7 here, you can clearly see that this 7 is greater than 5 and this 7 is lesser than positive infinity. It means that it is valid, right? It is valid, right? And if this is valid, then what I'll do, I'll go to the left subtree and I'll go to the right subtree, and I will check that these the node values which are present into the left subtree and right subtree, they are coming into my range or not. Okay, so let's say that currently I am standing here at this particular node. Okay, so again I have to draw the range. Okay, so see, if I consider this node 7, then this node number 6 is coming into the left subtree. Okay, so the value present into the left subtree should be lesser than 7. Okay, so I can say that any value which I have present here, it should be lesser than 7. Okay, it should be lesser than 7, and we can clearly see that this particular 6 is coming into the right subtree of this 5, right? It is coming into the right subtree of this 5. So from this point we can say that anything which is present into the right subtree should have value greater than 5, right? Should have value greater than 5. So this is the range for this particular node. And if we check the range, so here we have value 6, here we have value 6, and this value 6 is greater than 5, this value 6 is greater than 5 and it is also lesser than 7, it means that it is valid, right? It means that it is valid. Now if it is valid, then what do we need? We need to check the left subtree and we need to check the right subtree. So here we have null and null value. So if we are encountering a null value, it means that it is a valid BST. So what we'll do, we will return a true here, we will return a true here. Yeah, okay. So at this particular node number 6, we know that the left subtree is also valid, the right subtree is also valid, and this particular node value is also coming into the valid range. Okay. So now what I will do, I will return a true to its parent. Okay. So I will return true to this node number 7. Okay. And now I'll go to the right subtree, right? Now I'll go to the right subtree. So let's say that currently I am standing here at this node 8. Okay. So firstly, I need to check that the node value, which is 8, is it in the valid range or not? Okay. So see, we can clearly see that this particular 8 is coming into the right subtree of this 7, right? It is coming into the right subtree. What does it mean? It means that any value which is present into my right subtree, it has to be greater than 7, right? It has to be greater than 7. Okay. But if I try to write what should be the maximum value, what should be the maximum value for this particular node? So you will say that the maximum value can be anything, right? I can write here 2000, 2k, right? Or 20,000 or 2,000 or 200. It can be anything, but the condition is it should be greater than 7, right? It should be greater than 7. So let's say that the maximum limit is positive infinity, right? Let's say the maximum limit is positive infinity. So for this particular node, the minimum value, right? The minimum value for this particular node should be greater than 7 and the maximum value should be lesser than 8. Okay. So the value present at this particular node is 8. And if I compare it, if I check that it is coming into my range or not, so you can clearly see that this 8 is greater than 7 and this 8 is lesser than positive infinity. It means that yes, it is in the valid range. It is in the valid range. Now, if it is in the valid range, what I need to check? I need to check the left subtree and I need to check the right subtree. Okay. So here we can see that in the left subtree, I have a null value. It means that it is a valid BST. So I will return true from the left subtree. In the right subtree as well, we can clearly see that we have a null value. It means that it is a valid BST. So I will return true from the right subtree as well. Okay. Now for this particular node 8, we know that the node value, which is 8, it is coming into our range, right? It is coming in the valid range. And the left subtree and the right subtree are also valid BST. Okay. Now, if all these three conditions are getting satisfied, then what I need to do, I need to just return true to the parent. Okay. So I will return true to the parent. Okay. So now when I'm standing here at this node number 7, I know that this node number 7 is coming into my valid range. The left subtree of this node 7 is BST. And the right subtree of this particular node 7 is also a valid BST. Now, if all these three conditions are satisfied, then what I'll do, I will return true to its parent. Okay. So I will return a true to this particular node 5. Okay. Now, when I'm standing here at this particular node number 5, I have already checked that the value of this node 5 is coming in the valid range or not, right? So it is coming into the valid range, right? And I am receiving a true from the left subtree. It means that this left subtree is a valid BST, and I'm returning a true. I'm getting a true from the right subtree as well. It means that the right subtree is also a valid BST, right? It is also a valid BST. Now, if the left subtree is a valid BST, if the right subtree is a valid BST, and the node value is also coming into my range, it means that it is a valid BST, right? And if it is a valid BST, then I will simply return true. Okay. And this is the particular approach which we are going to use to solve this particular problem. If you have any confusion, if you have any doubts, then I would recommend you to do some dry runs by your own, take some different examples, and then you will understand this particular approach in a more better way. So we have discussed our intuition, we have discussed the approach which we are going to use. So now let's think of how we are going to code this particular problem. So as I always say, the coding portion is going to be easy, right? The coding portion is the most easiest part. Okay. So let's say that I have a function, and here I am receiving my root pointer. Okay. Here I am receiving a root pointer. So what should be my base case? See, I already told you, whenever we are encountering a null value, it means that it is a valid BST, right? So what I'll do here, I will write if my root is equal to null, then just return true, right? It is a valid BST. It is a valid BST. Okay. Now at every node, what I have to check? At every node, I have to check that the node value is in my range or not, right? The node value is in my range or not. Okay. So let's say I have two variables, right? I have a mini variable and I have a maxi variable. Okay. This mini and maxi are nothing but my range. Okay. They are nothing but my range. And initially this mini is minus infinity, and initially this maxi is nothing but my plus infinity. Okay. So see, I have to check that the node value has to be greater than mini and lesser than maxi, right? If it is greater than mini and lesser than maxi, it means that it is valid, right? If it is valid, then I do not need to do anything. But if it is not valid, then I need to return false. Okay. So now I will check for the not valid condition, right? I will check for not valid condition, right? I will check for not valid condition. So I will check that if this root value is lesser than or equal to my minimum value, or this root value is greater than, right? If it is greater than or equal to my maxi, or greater than or equal to my max value, it means that this is not valid, right? It means that it is not valid. And if it is not valid, then I will directly return false, right? I will directly return false. Okay. If this condition is not satisfied, if the root value, if the current node value is not in this particular range, it means that it is not valid. If it is not valid, I will directly return false. I do not need to check for the left and right subtree. Okay. Now, if this is valid, right? If this is valid, then this particular return statement will never get executed, right? And if the node value is coming into our range, right? If the node value is coming into our range, then we will come here, right? Then we will come here at this particular line. Okay. So see, if the node value is in the range, then what I need to check? I need to check for the left subtree and the right subtree. Okay. So here I will write bool left is equal to solve. Okay. I need to go to the left, right? I need to go to the left. Okay. But see, whenever I'm going to the left, then the value of this mini and maxi are changing. Okay. Whenever I'm going to the left or I'm going to the right, then my range is getting changed, right? My range is getting changed. Okay. So let's take this particular example to understand, right, how we have to change our range when we are moving to the left, right? When we are moving to our left sub tree. Okay. So see, for this particular tree, we know that it is coming into the left subtree of this 5. Okay. It is coming into the left subtree of this 5. Okay. What does it mean? It means that the maximum value should be lesser than 5, right? The maximum value, this is our maximum value. It should be lesser than 5. And what is this 5? This 5 is nothing but my value of the current node. Okay. It is nothing but the value of my current node. Okay. And what should be the minimum value for this node 3? The minimum value can be anything. Okay. So here we have minus 3. Okay. Sorry, here we have minus infinity. So what we'll do, I will just simply assign this minimum value to this, right? I'll just simply assign this minimum value to this when I'm going to the left subtree, right? When I'm going to the left subtree. Okay. I hope it is clear to you. So see, when I'm going to the left, then my minimum value will not get changed. Okay. Minimum value will remain same, right? Here also I had minus infinity, and when I am going to the left hand side, when I'm going to the left subtree, the minimum value will remain same. Okay. So the minimum value will be remained minus infinity, but the maximum value will get changed. The maximum value will get changed to the root value, right? The maximum value will get changed to the node where I'm standing. Okay. So I'm standing here at 5. So here I'll have 5. Okay. So now what I will do, at the place of maximum value, what I will return root val. Okay. I will return root val. So I hope it is clear to you. Okay. Now similarly, when I need to check the right subtree, then what I need to do, let me just make a call to the right subtree. So here I'll write root and right, root and right. Okay. Now let's think of the condition when we are moving to the right. Okay. When we are moving to the right. Okay. So firstly, let me rub this. So let's say that my root pointer is pointing here to this node 5, and currently I'm standing here to this node 5, and I am going to the right subtree, right? I'm going to the right subtree. So see, we know that whenever we are going to the right subtree, then everything which is present into the right should have value lesser than 5, okay? Lesser than 5. So what we can say that this 5 is nothing but my minimum value, right? This 5 is nothing but my minimum value. And if I talk about the maximum value can be anything. So it will be positive infinity. From where I'm getting this positive infinity? Nothing, but it is the previous maximum value, right? Previous maximum value was positive infinity, so I'll just pass positive infinity here as well. Okay, so now what I will do, the minimum value will be nothing but the current root value, and the maximum value will remain same. Okay, maximum value will remain same. Okay, so after checking for the left subtree and the right subtree, what I need to return, I just need to simply return left and right. Okay, I just simply need to return left and right. Okay, if I am getting a true value, if I am getting a true value from the left, and if I am getting a true value from the right, okay, then only I will return true, okay, else I will return false. So this was the approach, this was the code. I hope it is clear to you. Code is pretty easy. Okay, and if we talk about the time complexity, then if you clearly observe, then we are traversing each and every node only once. Okay, therefore the time complexity will be equal to O of n. And if we talk about the space complexity, then the space complexity will be equal to O of h, where h is nothing but the height of our binary search tree or a binary tree. Okay, and at max, in the worst case, the height of our tree can be equal to the number of nodes, right? It can be equal to O of n. So we can say that the space complexity in the worst scenario will be equal to O of n. Okay, so I hope this particular approach and code is clear to you. So let's fastly code it up on LeetCode. So here we are on LeetCode. Let's fastly code the approach which we have just discussed. So before that, let me just collapse this. Okay, so to solve this, what I need, I need a minimum value and I need a maximum value. Okay, so let me just take it in a long variable so that I will not have any problem with the range. Okay, so let's say I have long mini, and it is equal to my long min, right? Long min. And I have long maxi, which is equal to my long max. Okay, which is equal to my long max. Now what I'll do, I'll pass these values to a function. And it will return with the answer. Okay, so I'll write return solve. I will pass the root value as well, and I'll pass the minimum value, and I'll pass the maximum value as well. So now we just need to write this solve function. Okay, so we know that this solve function, it should be of bool type because it should return true or false value. So here I will write bool solve, and what are the values it is taking, right? What are the arguments? First is the tree node root value, and the second one is the mini, and the third one is the maxi. Okay, now what is our base case? Base case is very simple. If at any point my root is equal to null, then I need to return true. Okay, then I need to return true. So here I will check for the not valid condition, right? I will check for the not valid condition. So if at any point the root value, if the root value is lesser than or equal to the minimum value, or instead of and I'll have or the root value is greater than or equal to my maximum value. If this is the case, then I can just directly return false. Okay, if this is not the case, right? If this is not the case, so this is the code for valid condition. Okay, so if this is not the case, then only we will reach here to this line number 21. Okay, so now we need to check for the left subtree and the right subtree. Okay, so here I will write bool left is equal to solve, go to the left subtree, and when we are going to the left subtree, then the minimum and maximum value will get changed. Okay, so the minimum value will remain same, and the maximum value will be nothing but the root value itself. And similarly, I need to make a call for the right subtree as well. So when I'm going to the right subtree, I should pass here root right. And when I'm going to the right subtree, then the minimum value will get changed. Okay, minimum value will get changed. So here I'll pass root val, and here I will pass maxi. Okay, and after getting the left value, and after getting the right value, what I need to return, I just simply need to return return left and right. Okay, left and right. So this is our code. I hope it is clear to you. What we are doing here, we are using long instead of int, so that we do not get problem with the range. Okay, so here we have a mini, its value is long min, or you can say that in minus infinity, or here we are having a maxi value, or it is assigned with the long max. You can say that it is nothing but positive infinity, and we are just calling our this solve function, and we are returning whatever we are receiving from our solve function. Okay, so here at the solve function, firstly we have returned our base case, that if at any point root is equal to null, just return true. Okay, if we do not have any node present, it means that it is a valid BST. Okay, then here we have wrote the condition for not valid BST, that is if the root value is lesser than or equal to the minimum value, or if the root value is greater than or equal to a maximum value, it means that it is not valid. If it is not valid, then we can directly return false. Okay, now if it is valid, then we need to check for the left subtree and the right subtree. Okay, so whenever we are going to the left subtree, then the maximum will change, right? The maximum will become root value. And whenever we are going to the right subtree, then the minimum will get changed. Okay, minimum will become the root value. Okay, and at the end we are just returning whatever we are getting from the left subtree and the right subtree. Okay, so I hope it is clear to you. Let me just run this. So here you can clearly see that all the 4 sample test cases are running fine. Okay, so let me just submit this. So here you can clearly see that this particular approach is accepted, and I have already explained you the time and space complexities. But we also have one more approach to solve this problem, which I would like to discuss, but not in this video. So I'll make a separate video for that, another approach. But make sure that you watch both the approaches, so that it will help you in your interviews or in your online assessments. Okay, so I hope you liked this video. If this video was helpful to you, make sure that you liked this video and you subscribe to this channel. If you have other approach, make sure you comment it. And if you are facing any problem or any errors in this particular coding solution, then you can mention it in the comment. I will try to help you. Okay, so this was all for this day. We will meet again tomorrow with a new question.